Energy is the ability to do work. And like momentum, it's kind of abstract. Unlike momentum, energy has no direction. It doesn't make sense for energy to have direction. What does it mean to have 7 energies east? That doesn't make any sense. But you could say I have 10 energy. There's units to energy, which we'll talk about, but you can talk about a quantity, but talking about a direction doesn't make any sense. So if energy has no direction, what is it? It's a scalar. Cool. There are 2 main types of energy that we talk about in the world, in physics. Those 2 types of energy are kinetic energy. Kinetic energy is something for those of you who had a science teacher who taught this unit. Kinetic energy is the energy that comes from motion. Any moving object has kinetic energy. The faster you move, the more kinetic energy you have. E stands for energy. Ke is what we're going to call kinetic energy. Does anyone remember the formula for kinetic energy? Yes. Sorry, Diego, his hand was up first. 1/2 mass times velocity squared. So then the units for kinetic energy are what? That doesn't make any sense. Why would it be joules, random French guy? I'm pretty sure he was French. Was he French or was he? Oh, where was he from? Oh, I'm very wrong. He was not French. He was British. Why? Why does James Prescott Joule have the honor of having his name attached to energy? Kinetic energy. But you're right. It is the joule. But like everything, well, not everything, like lots of things in physics, just because it's something it's named after you doesn't mean that that's all it is as far as the units go. Newton's, we had another one for Isaac Newton. His 3 laws for forces gave us a fair bit to work with, so we named the units of force after Newton. But we also had another way to measure forces. Force was a mass times an acceleration. A mass was measured in kilograms, and acceleration was measured in meters per second squared. So we said that equivalently, forces were measured in kilogram meters per second squared. Energy is similar. Mass is measured in kilograms. Velocity is measured in meters per second. So a joule is equal to a kilogram meters squared per second squared. And that's complicated and gross looking. So James Prescott Joule gets to co-opt this and say, I don't want to look at this gross thing. Let's look at joules instead. And kinetic energy is easy. Here's a week of Science 10. A 5 kilogram object is moving at 7 meters per second. What's the kinetic energy? Well, kinetic energy is equal to 1/2 mv squared. A half's just a half. The mass was 5. The velocity is 7, and we need to make sure we square it. 7 squared is 49. 49 times 5 divided by 2 is, I'll just tell you the value, 122.5 joules. That's it. It really is that straightforward. So kinetic energy is easy. One of the 2 main types of energy we look at. The other one gets a lot more complicated because it's, as abstract as energy is, it's even more abstract. Potential energy. Now, potential energy is energy that is stored in, what does it mean to be stored in an object? What does that even mean? It means that your object has the potential to use energy later, given certain traits about the object? I'm going to Google that in German. You want to translate that?
I think for us it's location.
It's location?
Like we call it location.
Oh, don't Google anything yet. Don't know Googling yet. So what you're calling location energy. So potential energy is an overarching term. Potential energy is a little bit more complicated than kinetic energy. Kinetic energy is motion, period. Potential energy, there's a bunch of different kinds. So potential energy, we're going to look at three of them. Potential energy is location. So where you are relative, like vertically, your location. In English, we call that gravitational potential, which is the first one that we're going to look at here. So what you guys call location energy, we call gravitational potential. There's also potential energy other places too. If something has the ability to do work later, elastic band, not doing any work right now. But if I pointed at Vian, now he's uncomfortable. Why? Because if I let this go, at some point in the future, the potential exists for this thing to fly at Vian. Right at his face. Okay? So we call that elastic potential. We'll look at that one too. I have one of these kicking around here. Where are you? Is that guy doing any work now? No. But could it later? Yeah. So what about this thing? Doesn't anyone know how a battery works? What about this thing could do work later? Any Science 9 students in the room? Yes, Granavin, you remember? Yeah, due to what? No. There's a reason they flow. It is not magnetism. There's a chemical reaction. There is the setup inside here, and I'm not going to rip the thing open, but there's a setup inside here where you've got two different semi-insulating compounds. And if you allow the electrons to flow from one, if you give the electrons a path to flow, and a chemical reaction will take place. So a battery is just chemical potential energy, which we won't look at because that's a little complicated. You actually have to take chemistry for that one. You'll look at electrochemical cells in chemistry and why they work the way they work. And I'm sure there's more. There's nuclear potential energy. You haven't split the atom yet, but you could. And if you did, there's a lot of energy there. So we're going to look at these two this year. You looked at gravitational in grade 10. We're going to add elastic to that. And so yeah, like I said, we're going to concentrate on these two types. Gravitational potential energy is potential energy that exists on two types, these two. Gravitational potential energy is due to having a height above something. But a height above what? Like, I have a ball, tennis ball that we've been playing with periodically. Does it have any gravitational potential energy where it sits? What do you mean? So it could fall. If you remove the table. Okay. Okay. So I put it right on the edge of the table. Now what's our reference point? It's not the tabletop anymore. It's where? Well, the reference, now you're saying it's got, your gut says, if we remove the table, well, do I have to remove the table now, or just have to like, right? Like if I let go of it at this point right now, what's it gonna do? gravitational potential energy. Here, there's not really an argument. If I let the thing go, it's going to fall. Okay? Well, how about now? No, why not? It was on surface before, and you said yes. Well, this isn't zero altitude either. I mean, like, I have a window right here. I can prove it to you. Can remove the screen pretty easy. I can throw the ball out there, right? Like, the floor is here, but you're saying, so you said the tabletop, well, we could remove the table, now the floor. This is too big of a job, removing the floor?
I think I'm just assuming that it was like zero, like this is on ground floor, then yeah. Like it was like as zero.
Sorry? No, this is good. But we're not on the ground floor. You're right. If we were on the ground floor, we're not. We're near it. But you're right. If, like,
I'm just assuming that the ground floor is like higher than the ground floor.
is that a reasonable assumption? Because I can see out the window there. I can very clearly see we're not on it. But how likely is it for that tennis ball to just fall to what we would call ground? Fairly unlikely. Unless in this moment we have an earthquake of some magnitude that drops this building, which would be weird, summon earthquake. We're talking about it and all of a sudden it happens. I don't want it, that would be terrible. But we're in the best place for it, up top. All the people down below. We're up there, we're there. Just like this push so you said on the table, yes, but we have to remove the table. Here, obviously yes. Here you said no, but using your same argument from before, I mean, based on your reasoning, I could argue yeah. Wait, here's another question. Which one has more? If I have, so here I have the ball at this height. How much gravitational potential, if you had, it's not a number, like, some, a lot, like, give me some way to measure, like, let's talk about a quantity. How much gravitational potential energy would you say this ball has right here? Any? A little bit? How about now? More than it had before, because this one's only going to fall this far, but now it's going to fall this far. Okay? If you're talking about sea level, altitude, the ball hasn't changed. I'm still holding it at the height that I'm holding it at. How about now? Right? Like, how much energy, let's pretend the screen's not there. How much gravitational potential energy does it have now?
Quite a few.
Quite a few. Substantially more than before. The ball has not changed. If all we're talking about is raw altitude, that has not changed. I'm holding it at roughly the same height I was holding it before, but now it has the potential to fall a lot further. So gravitational potential energy is actually kind of convoluted in that sense, because gravitational potential energy is not due to having a height above anything in particular. It's due to having a height above some reference point. You get to choose. Choose has two O's. And so here's something really ridiculous for you that will actually be very, very useful mathematically. If this is where the ball is, and you say that your tabletop is the reference point, how much gravitational potential energy do you have? 0. If I say that the ball hasn't moved, I'll leave the ball alone. The floor is now your reference point. It has more than 0. I mean, we don't know necessarily how much. Actually, we can figure that out really easy because you guys all haven't done this a great time. Know that gravitational potential energy is calculated using one formula, mgh. So I can find the mass of the ball. Let's see over there. I can find the height of the thing. I have a picture over there, and I could multiply that by 9.8. We have a number for this. But relative to the tabletop is 0. How about relative to the ceiling? If that's 0, how much gravitational potential energy does that thing have now? Negative. And there are totally valid reasons to pick things like that. ceiling, for example, to be the reference point with which we measure gravitational potential energy. And when we look at some roller coaster problems, I'll show you what I mean by that. Hey, what's up?
Really, Penny?
Yeah, what's up?
Like what 5 series, like 100 polynomials and what Greg said, right? And let's see that. I don't need it now.
No, I'm done.
Okay, cool.
He's got the algebra one.
Oh, okay. Awesome. Thank you.
So it really is that arbitrary. You get to choose what place you want to call 0 and then measure your height from that. Mass is mass everywhere in the universe. G is G everywhere on Earth. It's H. And how you get to measure H, you get to choose. Where to measure from. And depending on the context, like if you go and take, those of you who decide to take Physics 12, you'll look at situations where the most amount of gravitational potential energy you could have is 0, and everything else is negative. And that's where we start looking at gravitational potential energy for objects in orbit, leaving Earth. We call 0 really, really far away because there's no gravity out there. But then as you get closer to Earth, your gravitational potential energy starts getting negative somehow, which is weird. At its most simple, if you can fall, you have gravitational potential energy. And you guys said it already, potential energy, gravitational. Sometimes it's given as PE, sometimes it's EP. I've seen both notations. Sometimes it's EU. I don't actually know why we use U for potential energy. I just know I've seen it. This one's equal to, you guys said it before, mgh. And if this is energy, then somehow it should have the same units that this one did. So let's do an analysis here of the units. Mass is kilograms. Gravity is, what are the units on gravity? Meters per second squared, because it's an acceleration, you betcha. And the height is meters. So if I multiply kilograms, meter per second squared, and meters, this is equal to kilogram meters squared per second squared, which is the same we had before. So this is also a joule. Even though we're measuring it differently, one was the energy for an object in motion. One was the potential energy for an object that could fall. We analyze the units and the units come out the same. That should be a little bit weird, but we love it. Either way, joules. If they're not both joules, we can't compare them. They're not both energy anymore. So you would have done this last year too. For a 10 kilogram object at rest at a height of 12 meters, so by saying that the height is 12 meters, what are we calling 0? There's an implication here in those words. Like everything we did last chapter, words have meaning. What are we implying here by saying the height is 12? So we're calling ground 0. Yeah. We want to find the potential energy. So potential energy, PEG, is the notation I like to use. Is equal to mgh. And mgh is your mass times your gravity times your height, above whatever or below whatever you're calling 0. So, I mean, I don't think that's an overly difficult calculation to do. I will do it for you. 10 times 9.8 times 12 is basically 10 times 10 times 12, which would be 1200. In this case, we're using 9.8, so it's going to be 1176. Energy is measured in joules, because it's easier when you're ready for the page. Okay, so that's gravitational elastic is the next one. Elastic potential energy is more interesting than gravitational potential energy because you're just dropping stuff. Elastic potential energy, you actually have to like hold on, because elastic potential energy is is due to energy stored in elastic material. And if you recall, if you remember back to last chapter, when we looked at springs, elastic potential is caused by doing what to materials? I'll give you a hint. Sorry? Distorting them. Oh, yes. Both of these together we call distorting. A simple way to talk about distorting is either by compressing, which is a weird way to say it, compressing, or stretching. And depending on the construction of the object, you can do one or the other, sometimes both. You don't really compress a rubber band, but there are springs that kind of have a rigid shape. You can compress them or you can elongate them. Shock absorber being an example of one. Now we need an expression for the energy of a spring. Let's see if we can come up with it. What was the formula for the force due to a spring? Let's start there. Kx. So we're going to need K. And we're going to need an X. But does anyone remember the units on K? Units on X was easy. X is an extension or a distortion. X is meters. Does anyone remember the units on K? Yes, newtons per meter. So if I take my newtons, so Kx was newtons per meter, and this one's in meters. If I just multiply these two together, it's going to cancel, give me meters. So obviously this is wrong. This is not done. Let's recall what a newton is. A newton is a kilogram. A newton is a kilogram meter per second squared. So by multiplying a kilogram per meter per second squared by a meter, I'm getting the squared that I wanted. But then I'm dividing the meters away again. So that undoes what we want it to do. So what do I need to do to my extension? We need another meter here. I need meters cubed in the numerator, so that when I divide away these meters again, it leaves me with the kilogram meters squared per second squared we want for energy. What am I going to have to do? What's the easiest thing I can do to this equation to have meters cubed pop out of the numerator here? Add another x. You betcha. Similar to how kinetic energy is half mv squared, spring potential energy is, and for not unit reasons, but for what seems like totally generic reasons, we're going to multiply this by half. For reasons that will become clear when some of you study calculus. If you never study calculus, just take my word for it. Spring potential energy is given by the equation 1/2 kx squared. Because K is in newtons per meter, which is kilogram meters per second squared, and this m squared, or divided by meters, this m squared here is going to cancel out with one of those and still give us our kilogram meters squared per second squared that we want. But the interesting thing here is now we actually have another unit for energy. If I look at just these pink ones that I'm multiplying together here, these pink ones here, this meters in the denominator is going to cancel with one of those two squared meters up top. And so what we're going to get here is that spring potential is actually given by the units Newton meters So a Newton meter is actually also equal to a joule. Which is weird and awesome. Because what's the implication here? There's another implication. What do we measure in newtons? And what do we measure in meters? Distances. So we've actually got another kind of energy that's going to show up here. Something that is a force times a distance. We're going to define that as work. We're going to skip this example here for a second. And looking at these units, we can draw a straight line, well, a curved line, because I want space for that example. A Newton times a meter is the same thing as a force times a distance. We're going to define a force times a distance to equal work done. But work done is also equal to energy. Just by looking at units, all sorts of interesting things pop out. I digress. Let's go back for a second and take a look at the spring potential calculation. The potential energy of a spring, or what is the potential energy in a spring, with a spring constant of 4,680 newtons per meter that has been expanded by 15 centimeters. So potential energy, PE spring, or PES, we have PEG, now we have PES, is equal to 1/2 kx squared. So calculating this is going to be 1/2. K is 4,680 newtons per meter. We like those units. We do not like these. If this is in newtons per meter, this one also needs to be in meters. Converting centimeters to meters, we have to do what? How many centimeters? Divide by 100. Good. Dividing that thing by 100, and we're going to get 0.15 meters. That's going to jump into our equation here, 0.15, and we square that thing. The potential energy that exists there, I'll give you the value, is 52.65 joules. So let's go back to the hand-waving argument I was making before. Before I was arguing that because we can see here that if I simplify this, this is going to be equal to a Newton times a meter. And if a Newton times a meter is also equal to what we said it was equal to before, it means it's also a joule, while a Newton times a meter is a force times a distance. This is how we define the concept of work. So work is a force acting over a distance to change. This is what you were a little bit about what you were talking about right at the beginning here, Dave. A force acting over a distance to change the energy of an object. So based on this definition of work is actually different than conceptually your definition of work. Yeah, can I have forward you for a second? Okay, so work is equal to a force times a distance. Diego, do you feel like you're doing work right now? A little bit? Why do you feel like you're doing work?
Because the box is pressing down on my arm.
Okay, and you're holding the box there. Do you feel like you're getting tired? A little bit? We should wait a little bit longer. Or, you know, we can just make the thing heavier. And you should carry this one too. Just hold that there. What else do we add? Throw this in there too. This is a bunch of extension cords. This is really heavy. Yeah, you're gonna do that one. Do that, right? But do you feel like you're doing work right now?
Yes.
All right, and so like conceptually, you can put that back down. Conceptually, you would say, yes, Diego was there. I just handed him a box and he's standing there. Diego felt like he was doing work. Things were getting heavier. His arms started to shake a little bit more. But from a physics perspective, did Diego do any work? No. Work is equal to a force acting over a distance. I very intentionally did not tell Diego to pick up the box. I handed Diego the box and I said, hold this. And he held it at the same level. Box didn't move. Once I gave it to him, the box was stationary. So the distance Diego moved that box was 0. According to the argument that I'm making here, if work is equal to a force acting over a distance, did Diego do any work? No. Lazy. No, right? So our conceptual understanding of work and the physics one is different. You need to separate those two. So let's say instead I'd ask Diego to push that box across the floor. Diego pushes the box across the floor with a force of 80 newtons along a surface that is 3.5 meters long. How much work does Diego do now? Well, let's take a look. There's the box I asked Diego to push. Diego is going to apply a force for reasons. Diego is going to push totally parallel to the floor. Because if Diego doesn't push totally parallel to the floor, this becomes way more difficult. And Diego's applied force was 80 newtons. This is Diego's applied force. So if we want to talk about the work Diego did, the work Diego did is equal to the force he applied times the distance he applied it. So that's 80 newtons times 3.5 meters. You do the math. 80 times 3 is 240. It's 280, yep. Joules. Let's say, though, friction is acting against the box. Friction's acting against the box at 8 with a force of 8 newtons. So let's add that. Force of friction, backwards. 8 newtons. How much work does friction do? Well, work is equal to a force times a distance. Sorry? Because you're doing 8 times 3.5? Yes, but even though, sorry? Yeah, why? Because even though joules, energy, is not a vector, force is. And so is displacement. The object is moving to the right. The one thing we didn't make clear was earlier, we made no assumption of positivity or negativity, because I told you energy is not a vector, we don't care about direction. But there was a subtle implication here. The box is moving in the direction that it's being pushed in. So if I call to the right positive here, my work done was positive. Now, because the force is acting back, the friction is acting back against the direction of motion, this is going to be negative 8 newtons times 3.5. Lena said that that's negative 28 joules. So if energy is not a vector, what does that negative mean? When we were talking about velocity, acceleration, forces, that negative was a direction. Energy is not a vector, energy is a scalar. What's the point of the negative? Yeah. Nope. Energy is not a vector. Friction is, but the work done by friction, work is energy, so work is also not a vector. So what does it mean that this work here is negative? It has real meaning, even though it's not related to the vectorness of it all. Yes, that's exactly what it does. It cancels out some of the applied work done. So Diego did 280 joules worth of work. Friction took some of that energy away. Transformed it into what? What does friction transform energy into? Heat. So now we can start talking about a concept called efficiency. Diego put in 280 joules, but he didn't get 280 joules worth of work out. He only got 280 minus 28. Net work is equal to the sum of the works. Well, 280 joules went in, 28 joules came out because friction was working against Diego. Friction's a jerk. And so what we're going to get here is that even though Diego himself put in 280 joules, only 252 joules actually got applied to the box. So how efficient was Diego being? I'll talk about efficiency in a little bit. Not 100% efficient, because, sorry? Is it 90%? Did you do the math? No, it's this one. The work that came out, it's 252 divided by what went in. It is 90% efficient. You betcha. Wait, we'll talk about efficiency in more detail later. This is 90% efficient. You were saying something here, Day. I couldn't hear you. Okay. If you remember, let me know. I'm not sure what you were referencing. Well, we were talking about how this wasn't totally efficient because Diego put in 280. Friction took out 28 in the form of heat. So this wasn't a completely efficient exercise. Diego is only able to be 90% efficient because even though this is what he put in, this is what we got out. That. Well, as close as, if we can get to truly frictionless, then yes, all the energy that goes in is what gets applied to the object, you bet. There is another way to find net work. Not network, one word, net work, two works. The sum of the works. If you look at what work is equal to a force times a distance. So if I want work net, I could just apply F net to this equation and get the same idea. So instead of finding the works separately and subtracting them, what we could have done is we could have said that net work is equal to net force. So I could have said, well, net force is the 280 that went in minus the 8 that came out times the distance they worked over. Sorry, it's not 280, it's just 80. My bad, that's a typo. Diego put in 80 newtons of force. Friction applied 80 newtons. 80 minus 8 is 72. 72 times 3.5 is 252. So you conceptually, net work could be the sum of the works. But net work could also be whatever your net force is acting over some distance. I think I'm going to pause it right there because there's a lot in this first little lesson here. I want you to flip a couple pages forward. There's a page here on work, power, and energy. Yeah. And I'm going to get you guys, with the time that remains, I'm going to give you a few of these questions to take a look at. This will not take you long. How much work is done? How much work is done? Yeah, these first 10 should be good. Oh, hold on. Dang it. No, I need to do one more thing really quick. I need one more concept here. Flip back to this page. I was so close. We're going to cut it right here, right above the graphs. So work is also, and I did kind of define this a second ago, work is also defined, it's defined as a force times a distance, but work is also defined as a change in energy. To change an object's energy, work must be done. This is called the work energy theorem. So work is equal to a change in energy, whatever kind of energy you possess. And change in energy is energy final minus energy initial. So, two examples, and then that really will be done. A 5 kilogram object is accelerated from 2 meters per second to 5 meters per second. What's the work done? Well, work is equal to a change in energy. So that's going to be an energy final minus an energy initial. What kind of energy are we considering here? If I'm talking about the energy, the work done to accelerate an object, what kind of energy are we considering? There's only three kinds: kinetic, gravitational potential, or spring. Which one is it? It's kinetic. So we're going to look at the kinetic energy at the end minus the kinetic energy at the beginning. Well, that's just going to be 1/2 mv final squared, because that's what's changing, the velocity, not the mass, minus 1/2 mv initial squared. The kinetic energy at the end minus the kinetic energy at the beginning is the change in the kinetic energy. So this is going to equal 1/2. The mass was 5. The final velocity is also 5, and we need to make sure we square that. Minus 1/2, the mass was 5. The initial velocity was 2, and we're going to square that. So how much work is going to be done to accelerate this object from 2 meters per second to 5 meters per second? Well, 5 squared is 25, times 5 is 125, and a half of 125 is 62.5. And then that's going to be 5 times 4 times 10. So this is going to be 62.5 minus 10. 52.5 joules. This is the work you need to do if you're going to accelerate a 5 kilogram object from 2 meters per second to 5 meters per second. Now we could do the same question a really convoluted way. We could find the acceleration using kinematics. We could find the force. We could figure out the distance it took to accelerate this object. We could multiply those two together and get the work done that way, or changing kinetic energy. It's really slick. Looking at work as a change in energy is really, really quite slick. We can ignore all the kinematic stuff we did in chapter 2 because it gets dealt with here with KE. And then really the last thing I'm going to do today is this. It's another example, but we're looking at lifting boxes. A 10 kilogram box is lifted 5 meters straight up. What was the work done? Well, work is equal to a change in energy. What kind of energy are we changing here? The object was here. Now the object is here. What have we done? We have changed the gravitational potential. Here it was 0. Here it's something else. So we're looking at the potential energy at the end minus the PE subscript GF minus PE subscript GI. the gravitational final minus the gravitational initial. So this is going to equal mg, m and g don't change, so it's going to be mgh final minus mgh initial. So if we call the initial height 0, and the beauty is we don't actually know what the initial height was. The ball could be here, and I raise it to here. The ball could be here, and we raise it to here. As long as the distance between the two positions is the same, it doesn't actually matter where the object started. So we're going to call the initial height 0 regardless of where the object was. It doesn't say the box was on the ground. It just said it was lifted. So mass was 10, g is 9.8. The final height is 5 minus 0. That's going to be 490 joules of work done. And now I'm actually done. Now I want you to flip the page. We'll leave the graphing stuff and the power stuff till tomorrow. By tomorrow, I mean Monday. I want you to look at these first 10. There's not a lot of work here, even though there are 10 questions. I want you to do all of them. There you go. You have 2.5 days to do them. Well, 2 full days. Well, no, you have till midnight tonight, and then another 48 hours to get those 10 questions done. Oh, I don't care what you. Just because you're choosing to sleep doesn't mean the time's not available for you to do physics.